Hi everyone. So today we are going to continue talking about limits, and we're going to explore something called the squeeze theorem. The squeeze theorem works in a very specific set of instances, and what I'd actually like to do, you can see the wording for the squeeze theorem here. We're going to talk about that in just a second, but I'd actually like to flip your paper over. There's one lonely example here on the back of your page. It's actually example 3, but it got pushed to the bottom of the page here. And I'd like to use this as sort of a demonstration of how the theorem works before we've even talked about what the theorem says, and then we'll go back and talk about the wording of the theorem. So we're trying to find the limit of this thing as we're approaching 0, okay? And it's actually telling me that the answer is 0 and it just wants me to prove it, but let's pretend we didn't know that for a second. Let's pretend we're just trying to find what this limit is. Well, I want to plug in 0, and that would work out okay here, but when I go to plug 0 into this function, I get something that's undefined, okay? This is sort of one of those indeterminate cases where I'm not sure what the limit is. There's a hole in the graph or some sort of discontinuity that's preventing me from finding my answer. So here's what some clever mathematician came up with at some point. I'm going to start by just looking at that sine piece. So the sine of 1 over t. And I know I can't make t a 0, right? But other than that, this is just a sine function. This is sine of something. And the input's a little bit non-traditional here, but it's still a sine, right? We're taking a sine of something. And if you think back to trigonometry, the largest sine could ever possibly be is 1. So this thing here has to be less than or equal to 1. We can also say that the largest it could ever be, or I'm sorry, the smallest it could ever be is -1. So this thing has to live above -1. So we know that this function, this piece of the function, no matter what, lives between 1 and -1. Okay, so now I need to figure out a way to incorporate this t squared. So I'm going to come down to this inequality that I've set up and multiply the entire thing by t squared, which is fine as long as I do it to everything, right? So -1 times t squared is -t squared, less than or equal to. Now I'm going to throw t squared in that middle function, which brings me to the function that I actually wanted to look at. And then that's less than or equal to just regular t squared. So now I want us to think about the limits of these functions. So remember, we were trying to find the limit as we're approaching 0. I want to find the limit as t is approaching 0 of really all 3 of these functions. But I'm going to do it to this guy, and I'm going to do it to this guy. And this is bad notation here, but I'm just going to say I'm squeezing this in as t is approaching 0. And my hope is that that will help me find this limit as well. Okay, so the limit, I don't know why I bothered squeezing it in because I'm just going to rewrite it anyway, as t approaches 0 of -t squared. Well, anytime we're finding a limit, the first thing we should try is just plugging in the number, right? So if I plug in 0, I get that this limit is equal to 0. Okay? Same thing over here. If I take the limit as t approaches 0 of just regular t squared, well, when I plug in 0, that's also 0. And this should make sense visually, too. This is an upside-down parabola, and this is a right-side-up parabola, but at 0, both of them are approaching 0. Okay? So we know this value over here is 0. And so what we now know is that our limit that we're looking for, this limit here, as t approaches 0, of t squared times sine of 1 over t, has to live between 0 and 0. Well, what's the only possible thing that lives between 0 and 0? It has to be 0, okay? And so this right here is how we're showing that this is true, that this statement is true. So here's what the squeeze theorem says in sort of layman's English. The squeeze theorem says that if you have a function that lives between 2 other functions, so like this one does, this lives between these 2, or actually this is probably a better one to look at. This lives between this function and this function. And the limits on either side are the same, then because this one is stuck in between two numbers that are essentially the same, this middle one must have that same limit value. So let's look at a picture to kind of verify that. You look at the front side of your page here. I'm sorry, usually I have one that's in color, but this here is the graph of y equals x squared, and this is the graph of y equals negative x squared. This is actually really similar to the example we just did. The only difference is this is looking at a cosine function, so you'll see x squared times cosine of 1 over x, but all the math would work the same here. You can see that our function is kind of living in between these other two, and that these other two are both approaching 0 in the center, so this function in the middle must also be approaching 0. Okay? So if we have this sandwich situation, right, where f of x is squeezed in between two other functions, okay, and the limit of this one is equal to the limit of this one, then the limit of the middle one must be that same thing as well. And so actually, this says limit f of x, this should be equals L as well, like this. This should be the same, okay? Just a quick word on how to justify things, and this is in general in calculus. When you're using a theorem to justify, and we're going to do this quite often, the most important thing is you have to state the conditions of the theorem. The conditions are the if parts. So we would have to say, hey, we know this is true, and possibly we might have to say how we know it. I mean, in this case, it's just given to us. And then we would have to state that this piece is true. And then once we have our conditions, we can say, okay, now we know that this must be true as well. Okay? So when we do our justifications, we're going to say, since this is true and this is true, then this is true as well. Okay? So looking at example 1, we've got 3 functions. Here's that first part, right? That sandwich piece. These things are all sandwiched together. And I want to find the limit as f of x is approaching 2. I don't have any information about f of x, so I'm going to look at the limits on these guys. I'm going to look at the limits of g of x and h of x at 2. Okay, so let's start here with limit as x approaches 2 of g of x. Well, all I'm going to do is plug the 2 into g of x because that's the easiest way to find a limit. 2 cubed is 8, so I'm going to make this negative 8 over 3. 2 squared is 4, and then minus 7 over 3. And let's just practice some mental math here. So negative 8 minus 7 is negative 15, so that's negative 15 over 3, which is otherwise known as negative 5. And so we have negative 5 plus 4, which is negative 1. So this limit is equal to negative 1. I should say this limit is equal to negative 1. Let's do my other one. Limit as x approaches 2 of h of x. Well, that's just going to equal cosine of, and pi over 2, and then if I put the 2 in here, the 2's are going to cancel. And so I really just end up with cosine of pi. Think about your unit circle for a second. Cosine of pi is just equal to negative 1. So now this limit is also equal to negative 1. So this limit is negative 1 and this limit is negative 1. Therefore, we can now say that this limit back here must be negative 1. And I'm able to say that without knowing anything about the original function. Okay? All I did was prove that the functions on either side of this thing are always equal to negative 1. Okay, let's try one more. You may want to pause the video and try this one on your own. But I'm going to do the same thing. I have the first part of my if already established. We already know this is true. Okay? Now I need to prove that second part where we're saying like that one limit equals the other limit. So we need to find the 2 limits. So let's do limit of g of x as x approaches, where are we going? Negative 1. And then limit of h of x as x approaches negative 1. And let's plug some numbers in. So negative 1 squared is just 1, so this gives me a negative 1/4. If I put a negative 1 in here, negative 1/2 times negative 1 makes a positive 1/2. And then negative 1/4 plus 1/2, this is like 2/4, so this makes a positive 1/4 as my answer here. Let's check out the second one. So for h of x, negative 1 squared is just 1, so this ends up with a 1/3. This will be 2/3 times negative 1, so I'm going to say minus 2/3. But then I have a plus 2/3 on the end. So these guys cancel and I'm left with just a 1/3. Okay, we've got a breakdown here because this has always worked where these two things have come out the same, and this time it hasn't. That's inconclusive as far as where my limit is, but that's different than DNE. I'm not saying that there isn't a limit of this magical function f of x. Okay, there very well could be. We just can't pin it down because these functions don't squeeze quite close enough together. Okay, so we could say we know our limit lives between these two numbers. We could say, for example, that, is that negative? No, I keep trying to throw negatives in where they don't belong. 1/4 is less than or equal to this limit, which is less than or equal to 1/3. Like, we know that it has to live in between there. That's the best we can do. We don't know what the actual limit is. The biggest mistake I see with these, and this wouldn't be so much for this example, but let's suppose I had done this with another set of functions and I had found that this limit was 3 and this limit was 5. Can you think for a minute what most people are going to assume f of x is? And if you're thinking 4, it is not 4. I mean, it could be. Like, it's possible that it's 4. It's also possible that it's 3.2 or, 5.3 repeating. No, not 5.3 repeating. 4.3 repeating. Okay? It's possible that it's exactly equal to 3 or exactly equal to 5. And it is possible that it's equal to 4. But the best we can do is say we've got our limit narrowed down to a range of values, but without the two functions actually touching, we can't nail it down any further. So we can't really answer this question specifically. We can just give a range of values here. It's got to be between those two. I think that's about it on our friend the squeeze theorem. So if you do have questions about this, we'll work more on justifying as we work through some homework problems. But please let me know in class and we'll talk about anything you need to.